Okay, I'd briefly like to cover the concept of complementary spaces. Especially I'd like to consider linear functions for which the kernel and image are complementary spaces. It should be noted that this is not the case for all linear functions or functions in general, but only for a specific type of linear functions. So we consider a linear function phi mapping from V to V, and we impose a further restriction, being that the composite of phi with phi is simply phi. Okay, I'd like to add that there are indeed linear functions for which this property is true, which are not the identity. Okay, what do we mean by kernel and image being complementary spaces? We say that the kernel of phi intersected with the image of phi is equal to the null space, and furthermore we say that the sum of the kernel and image, they span the entire vector space V. So in order to prove that kernel and image are complementary spaces, we need to prove these two properties. Okay, so I'll begin with the first one. So proofs of this kind always follow the same pattern, if you like. What we have to prove first is that the null space is contained in the intersection of kernel and image, and this obviously is true because for linear functions phi we know that the zero is mapped onto the zero, right? So as you can see that first of all the zero is within the kernel as phi of 0 is equal to 0, and recall that the kernel is simply the set of V in V such that phi of V is equal to 0. And furthermore, obviously the null space is also in the image of phi, because as you can see we can plug in a vector such that we hit the 0 vector, right? So again, the image of phi is the set phi of V such that V is in vector space V. Okay, but now the other way around, what we also have to show is that the kernel of phi intersected with the image of phi is a subset of the null space. And how do we go along about this? Well, what we do is we simply consider vectors which are contained in this space. What do we know about vectors of this kind? First of all, they are in the kernel. So we know that if V is inside this vector space, then we know that phi of V is equal to 0 as V is in the kernel. And furthermore, we know that there exists a W such that phi of W is V, because V is in the image. So let's consider the vector V. We can rewrite this as phi of W because of this property, as V is in the image, and we can rewrite this in this way, since in case you've forgotten, but at the beginning of the video I said that we only consider functions where this holds true. So obviously phi of V is the same as phi of V, right? Now this we know is equal to V because we know that W is mapped onto V. Thereby we can simplify this to phi of V, and this equals to 0 as V is in the kernel of phi. Okay, so by this we have proven that the kernel intersected with the image of phi is equal to the null space. Right, now for the second property, we want to show this property, right? That the sum of the kernel and image are equal to V. To show that, what we do is, well, we first begin by proving this property. Well, we say that the kernel plus the image of phi are subset of V, and this holds true because obviously the kernel itself is a subset of V and the image itself is a subset of V, right? thereby their sum will also be a subset of V. Okay, but the other way around, if we say that V is a subset of kernel of phi plus image of phi, this is not so trivial. But what we can do is we consider a V in vector space V, and we can rewrite this as V minus phi of V plus phi of V, okay? And we'll just define this as Y and this as X. And I'm calling right now that X is in the kernel of phi, which you can easily verify by considering phi of X. We know that this here has to be 0, right? Because X is in the kernel. What we simply do is we substitute for X. So we say this is the same as V minus phi of V. And this is obviously phi of V minus phi of V, because phi is linear. And again, here you can see that this is the same as phi of V because of the property that, that phi, composite phi, is simply phi, right? And thereby this is phi of V minus phi of V, and this is then 0, right? So what we've just shown is that any vector V can be written as the sum of x plus y, where x is in the kernel of phi and y is in the image of phi, okay? So it follows that any arbitrary vector V in vector space V can be written as a sum of a vector in the kernel and a vector of the image. And to show you that this, so that there are functions which fulfill this property, which are not simply the identity, so meaning that phi of x is equal to x, right? But for instance, consider the matrix A being 1, 0 and 0, 0. Then you can see that A times x is the same as A times x if you plug in any vector x in R2, okay? So we can calculate this. This is, let's call the vector xy, right? Then this is simply x0, right? And if you now again apply the matrix A, then you'll see that this is equal to x0. Okay, so and this is A times xy, right? So as you can see, there are indeed functions or linear functions represented by the matrix A which fulfill this property, and for these functions the kernel and image are complementary spaces.